Hello, everyone. I'm Sanketh Srinivas. I'm the product manager for Microchip's CXL memory controller solutions. And today we have Tam with me, who is the product manager for our switching solution. So today we wanted to just keep it at a high level and talk about um, the compute memory bottleneck and how CXL is enabling to address the bottleneck and some of the use cases that CXL enables, right? To start off with the shrink and process node technology, the CPU vendors are able to cram in more cores onto a single SoC. However, the SoC package size is limited, and we're limited by I/O size, the I/Os rather than the die size. So essentially, cramming in more memory to enable the compute resources is a challenge. So how do we solve this? Right? So one way to address this would be with CXL, right? Uh, so also along with the memory bottleneck created by adding a ton of CPUs on the cores, we also have heterogeneous computing, which is known to work more performant with the AI and ML workloads. So what is hetero architecture? So essentially you have the CPUs, GPUs, and accelerators now competing for the same memory resources that was once only used by CPU. So in order to fix this or help with addressing the bottleneck, CXL comes into the picture. So CXL essentially allows memory disaggregation. So it's essentially simple. What it's doing is taking the DDR memory channel and moving it behind the I/O bus, which works on PCI electricals. So we are taking the DDR memory channels there, which is in orange, and moving it behind the CXL. So it takes a DDR DIMM, which is a pin count of around 200 plus, lowers it down to around 20 pins, and now you can scale the amount of memory that you can connect to a single SoC. So that's one of the use cases. There are multiple ways, like Vince spoke about the fabrics. So there are multiple system architectures that can be implemented with CXL. As the CXL spec progresses, we're seeing new system architectures that can be implemented. The first case is essentially the CXL memory expander case, which essentially adds capacity, bandwidth, and also enables a cheaper expansion of memory, right? So why leave it at that? So you can make the memory controller smarter, so you can enable the memory controller to connect with multiple hosts. So the memory controller can also have DRAMs connected behind it. So based on the host requirement, the memory can be dynamically allocated. So this enables with TCO. Essentially, there's a Microsoft paper out there talking about how much memory resources are stranded. So this enables to reduce the memory standing problem and improves the TCO by dynamically allocating based on what each individual host requires at any point of time. This next use case is, again, advancing the pooling a bit, sharing, right? So sharing will enable us to reduce host-to-host communication. So within the memory pool, now you can reserve spaces as shared memory spaces, so multiple hosts can share that memory space and access to it and own that memory space. So a host here can be a CPU or a GPU or accelerator. So if an accelerator traditionally had to access memory that's owned by CPU, it has to talk to the CPU, and it's really inefficient because you're just talking to fetch data from the CPU. So this enables to reduce that overhead and enable efficiency with system architectures. So extending sharing is global fabric is attached memory or a fabric memory. So with a single memory controller, you'll be limited to how many hosts you can connect to. So what Fabrics enables is to increase the number of hosts. So you're going to connect a host to a switch fabric as shown in this picture, and to the fabric itself, you can attach memory, which will enable you to efficiently use memory across the fabric. So this essentially changes the traditional memory model, or the pyramid, as we all know, right? So traditionally, we had the on-package memories like HBMs, L1, L2, L3s, DRAM, where hot data was stored. Then we had the storage class memory, and a mix of DRAM and storage class memory. So now what this pyramid translates into is you have the on-package memory, then you have the direct attached memory, then you have the CXL direct attached memory, then the next tier would be switch attached, and the last tier would be global fabrics attached memory. So along with these system architectures, what CXL enables us to do is also provides a unified interface irrespective of what memory is behind the controller. So there, one of the challenges with, for example, NVDIMM is enabling the support for it in the ecosystem. What CXL does is it gives a unified interface for the ecosystem vendors to integrate in their development flows. And behind the CXL controller, you can have DDR4 DIMMs, DDR5 DIMMs, or even have flash for example, the Optane replacement. However, so one thing to note here, each of these, even though it feels the same, the performance is going to be different. As long as the software or the application layer recognizes the performance and understands which tier it needs to place the data in, you can make this work much more efficiently and with a lot lower cost. So this is an example of how a fabric would look like. So in the picture, you can see there are multiple hosts, and each host will have its own Type 3 CXL memory expansion device, and also the host will be connected to a CXL fabric. The CXL fabric will have its own GFDs. So the GFD is essentially global fabric device. So where each GFD can have different memory types. So since now it's a pool based on where you want to place the data and how much capacity you want to enable to each host, you can very efficiently design a fabric and take it into and reduce your TCO. So from a performance perspective, right? So what do the latencies of these different tiers look like? For a traditional DRAM, the latency is around 100 nanoseconds, right? So the DDR controller on the CPU itself, it's estimated to have a latency of around 70 nanoseconds, and the DRAM component is around 30 nanoseconds. So for a direct attached CXL, let's assume the memory controller adds a latency of 40 nanoseconds. The DRAM will add another 30 nanoseconds. The CXL stack itself on the CPU, we can assume, adds around 100 nanoseconds. So the total direct CXL latency will be around 170 nanoseconds. So now for a pooling and sharing solution, because there's a lot more that the memory controller has to do, the latency will increase a bit. It's going to be around 70 nanoseconds, and that path will have a total latency of around 200 nanoseconds. Further, for a fabric-attached memory, again, based on what memory type you use, it's around 320 nanoseconds. So at Microchip, in order to enable this CXL implementation, we're currently sampling our first-gen CXL 2.0 devices, right? So our controllers are one of the, or the lowest latency memory controller out in the market with very high performance. We have enterprise-class RAS features, essentially enabling advanced CCC, data integrity, and also enabling functions like diagnostics, scrub, and BIS to ensure you manage the DDR memory appropriately. We have leading edge security with secure boot, firmware attestation to enable secure implementation of it in the data centers. We also interop with the ecosystem. So essentially, we talk to all the CPU vendors out there and also memory vendors to ensure a product is really stable and reliable and can be taken into deployments. We provide media independence. So one of our key things is we support both DDR4 and DDR5 today, enabling either a performance solution or a TCO-based solution. So with that being said, I'll hand it over to Tam to talk about switching a bit.
Thank you, Sanketh. So as Sanketh has mentioned, we belong to part of what we call the data center solution team. And one of Sanketh's products is mainly focused on CXL memory controller. So that's not the only product that we have. So we have another product called the PCIe switching right now. And based on the current generation, which is Gen 5, but we've been shipping Gen 3, Gen 4 for many years, and Gen 5 is now in production. And going forward to our next generation, which is PCIe Gen 6, and it is essentially going to be not just PCIe, but also going to be able to handle CXL switching. And at that time, I think we're going to be going back to CXL 3.1, even though right now our spec is 3.0. And it's going to be a whole new ball game because taking forward from our current Gen 5 PCIe switch, we're going to have integrate many CXL functions that basically allow customers to has the flexibility to either select PCIe or CXLs based on your requirement. So it is going to be a big programmable and allows you to connect to multiple hosts and memory devices depending on your use cases. And the key things for a CXL switching is they provide low latency, and we try to either beat the specs of CXL for latency, for .cache and .mem functionality, but we also allow you to interface to many devices such as CPU, GPU, and memory modules based on whatever is in the market at the moment. So currently, it allows you to basically share memory data, memory pooling and memory sharing based on the CXL specs. And whatever the CXL specs that's required, we plan to implement all the functionality into our PCIe and CXL switch. By that time, I believe it's going to be 3.1, but currently we're still going to mention it's a 3.0 switch because 3.1 is not officially out yet. So I cannot mention it's going to be a 3.1 compliance. And so it will support both upstream and downstream, similar to our current PCIe switch does. One thing is that it will support many types like Type 2 and Type 3 devices based on the CXL requirement. And you're allowed to cascade different switches. And it's basically you can connect to either a CXL endpoint or a PCIe endpoint. So it is quite flexible for the end user to configure the switch depending on whether your data are actually PCIe or CXL. Now, one thing I want to mention that I think the previous presenter said that it's going to be a highly complex system for PCIe Gen 6 because the encoding is PAM4 and not NRZ. So all the previous generation from Gen 5, Gen 4, Gen 3 has different encoding, and now PAM4 add one more complexity to the SerDes itself. But since we have already done many SerDes generation, we feel confident that we're going to have enabled this next generation SerDes coming up there. And our CXL and PCIe Gen 6 is going to be taped out next year around July, June timeframe. And it's hopefully we'll have the sampling at the end of 24, early 25, based on how fast the market is moving. But the ecosystem from SoC, CPU, and it's going to be around that time frame. So if you look at all the CPU vendor out there, they're going to have their Gen 6 PCIe and CXL devices available at around late 24 and mid 25. So we believe that we're going to be meet all the schedules requirement for the ecosystem that's out there. So if you look at a interconnection for CXL compared to PCIe. So PCIe is a top-down topology. So it's more like a tree. And even though our current Gen 5 PCIe switch, we allow customer to build a complex fabric through the what we call the advanced fabric switches, and that gives you more flexibility to connect like host to host, SRIOV and multi-host interfaces. That means you can connect one domain of host to the other domain endpoint or the other domain of host. But given that CXL is coming out, our next generation is going to be moved from a proprietary fabric switch into a CXL fabric switch. So because it's going to be open standard and not based on a Microchip's proprietary advanced fabric interface. So currently Gen 4 and Gen 5, we have the advanced fabric switch, which is proprietary. But moving forward to CXL and PCIe Gen 6, we're going to adopt the CXL fabrics interfacing so you can connect to either multi-host, peer-to-peers, memory pooling, memory sharings. So based on CXL standard, that's going to be available by that time, either 3.0 or 3.1, depending on when the final spec is going to be released for 3.1. So this is going to give you a very flexible interconnects through our switch. And here's some of the typical comparison between CXL 2.0 switch and 3.0. So 2.0, you can see that it's a single layer switching. You connect from host to endpoint. Very simple. You cannot do a whole lot through a switch. But once CXL 3.0 is out, then you can actually cascade in multiple switches and do highly complex fabrics interconnections based on how you want to interconnect your host to multi-host applications. And looking at the fabrics of CXL 3.0, we can see that the key advantage is allow customer to configure how complex you want to. So the interconnection is up to the end user's imagination. So it's a flexible switch that we're going to be providing. And with that, I think this is the last slide I want to say is that we had carried forward all the technology from a previous generation, from Gen 3, Gen 4, Gen 5, and now moving forward to Gen 6 and CXL, which is a new territory for many chip vendors at the moment, where CXL is new. But we think that CXL is going to be the next generations of interface protocol besides PCIe. So PCIe will not go away. I think that PCIe and CXL will coexist side by side in the next generation moving forward. With that, I will end the call. Thank you for participation. Any questions?
Thank you, gentlemen. If you can just set it there.
The question?
Looks like this.
Sorry, quick question. So, how do you enable CXL memory expansion? Is it just plug and play, or do you make any firmware modifications or anything?
Can you repeat the question? Yeah.
How do you enable CXL memory? Is it just a plug and play, or do you make any modifications and settings in firmware?
Okay, so first of all, you know that both PCIe and CXL, they share the same physical layer. And in our switch, we have a process to allow you to program, and either it can recognize the packet, whether your protocol is PCIe or CXL, and depending on if you CXL, you want to do memory pooling, memory sharing, then you can configure the switch to do that.
Okay, thank you.
Okay.
Question?
Yeah.
Hi, this is Nilesh. I just had a question in your topologies. I noticed you didn't show retimers. So are you seeing, like in the typical deployments at hyperscale or enterprise, there's going to be a need for retimers?
Yes, good question. So retimer depends on how long your trace line is. If your system is short, then you may or may not need retimer. But if you have a large system, yeah, you do need retimer, especially when you go past Gen 5 and running at 32 to 64 gig. And if your circuit trace or cable is long, you definitely need a retimer for that.
It's just a follow-up question. So in the deployments that you're seeing or you're anticipating or hearing from customers, is that like 100% of the case or like just 50%, or is it just like 1%?
Yeah, but retimer is a necessary evil, but no, that is an expense that nobody wants to put onto it. But again, currently I see that in a large system they do require retimer for even to Gen 5, and if your system is small enough that you are meeting the channel reach of your product, then you may not need retimer. But still, you may have to use high product, what you call high quality PCB traces in order to satisfy the signal integrity. But overall, I see that currently in Gen 5, especially in the AI ML system, they do need requirement because those systems are huge. They run long traces and big backplane and everything else. So they do need require a retimer.
Thanks.
Thank you. Any other questions?
Quick question. In a GFAM system environment, do you expect GFAM is implemented in a PCIe cable based or Ethernet based?
More
in practical sense?
PCIe based.
We're talking about hundreds and thousands of computing nodes connected, right? Do you think it's feasible to connect through PCIe cable?
Right now, we believe that PCI cable handle GFAM. Yes.
Yeah, and another question is your latency target for 40 host side 100 nanosecond, memory controller 40 nanosecond, DRAM 30 nanosecond. Is it your current target? I think the current system, serial system, does not satisfy that latency target.
You talk about
What
the
is your plan?
latency of the host to endpoint, or what's?
Yeah, so from host to the end DRAM side, including everything. So my measurement is exceeding all those numbers. So.
Yeah, I mean, we cannot define law of physics. There's going to be, once you go through a silicon chip, there's always some delay latency right there. But we try to design the way that it is minimize the amount of latency through the switches or memory controller. So that's the key factor that everybody need to deal with. We can't fight the law of physics.
What's the current number of your memory controller, CXL controller?
Oh, memory controller, you want to answer that?
CXL controller latency.
So that's a secret sauce, right? We'll have to talk
Yeah.
under NDA on that. But that's where we see the industry going, and we're very close to those numbers that we showed. And we believe we can achieve these targets.
All right.
All right, guys. Thanks.